Go ahead. You might have to order it online through the online bookstore. I don't know what else to tell you on that. Um, yes. Huh? Okay. All right. So, what we're talking about today is raising a number to a power, and it's a little bit more complicated than that because the main thing we're going to be talking about is the metric system when we do a lot of this. Okay? So, how many of y'all remember exponents? A few of y'all? What is an exponent? All right, better question. What is an exponent supposed to mean? Yes. How many times you take that bigger number, the lower number, and multiply it by itself? Correct? Okay. So the larger number is the base, the smaller number is the exponent. You multiply the base number by itself as many times as the exponent tells you to. So if you have a 3 as a base and 4 as your exponent, you're multiplying 3 times itself 4 times to get 81. 4 to the third would be 4 times itself 3 times to get 64. 5 squared is 25. 2 to the 5th power is 32. Any questions on that so far, guys? Everything kind of seem familiar? All right. So most of us know that if you have an exponent of 2, it also means that you are squaring it. Why that term is squared, I don't know, but it is. Just like every other term. Why do they call it a quotient? Somewhere in history, somebody said that that's the term they wanted to go with. If you do to the 3rd power, that means it is cubed. So you go from a square to a cube. Again, could not tell you why for the life of me. And I've had people ask me, why is that the term? I'm not, I teach engineering and electricity and electronics. Mathematics, not so much. I'm trying to help y'all get base mathematics back in your brain because I know a lot of y'all haven't seen a lot of this since, for me, it would be over a decade since I graduated high school. That's pretty typical for a lot of people we come into classes with. So, but things like why do they call it cubed? I could not tell you. Somebody decided that that was the idea of what they wanted to say. All right. So in your calculator, by the way, how many of you have got a calculator? First, let me ask that. A couple of you. Okay. I got to figure out what happened to mine. At some point, I've set it down and it has just come up here. Fairly typical because every time I turn around, I lose another one. But yet, I still have some that have left over from when I was in middle school and high school. Don't ask me how some of these have lasted and some of them have not. But all the same, I can find these pretty much about less than 20 bucks. I've gotten them at Target. I've gotten them. Target's the most common one. You can get them off Amazon pretty cheap. My personal preference tends to be Texas Instruments. Some people prefer Casio. As long as it has the ability to do sine, cosine, and tangent, especially if you plan to take AC electronics and electricity, then you're good. If you're simply planning to take this class and DC and maybe a few other minor ones, sine, cosine, and tangent are not critical. But the reason I kind of like this one right here, the 30x2, the fact that I can do fractions with it, I can do exponents with it, can do a lot with it. Not to mention, like I said, that thing's lasted me since middle school. The fact that I've kept up with it that long is probably the most amazing part of that little sentence. Yeah, pretty much. Then again, I was also the kid that stuck everything back into my binder, and then once school ended, left everything in that binder until the next year. So you have a couple different keys on most calculators. I have not seen a calculator in years that did not have the square key. That's where it says x to the 2. All right? I have found calculators that are like $2 that still have that square key on them. Okay? But the key that you mainly want to use, especially dealing with exponents, there's a couple of them on this particular calculator. That's the reason I kind of know this one so well. Excuse me. And this particular one has a raised key. And that's always a nice one to have. And at some point there is an x to the y key or the e to the x key. There's generally some way to raise it to the power. Okay? All right, so how many of y'all remember to find the roots of a number? What it means to find the root of a number? Basically, it means that you're looking for whatever number. In this case, if you're looking for the square root, what number times itself twice gave you that number, right? That's kind of familiar to everybody? So the small number inside what's called the radical is the number of, I'm sorry. So the symbol is the radical, for which it's used to tell you to find the root or base of the number. And this number is supposed to tell you how many times the base number was multiplied to get this number right here. Okay? So what times itself twice gives you 9? What times itself twice? Not added. Times.
3.
3.
3. 3.
Yep. Everybody, how many of y'all remember having to do the times tables in, I think, 5th grade? Where they timed you to do the times tables, right? How many people thought that was probably the most evil thing they could give you as an assignment? This is your test for the day. We're going to time you for the next 10 minutes to remember all these times tables. If you get test anxiety at all, you were sunk. Lord knows I was. God, that was always one of the roughest things they did. All right, moving on. Finding the root. Pretty much we've already done that. I'll go ahead and tell you guys now, I won't be really doing a lot of finding the root. This is all good stuff to know, but it's not going to be something that we go truly in depth on here. And if you do have it, I'll let you use your calculators for it. So square roots, finding the square root key. On a lot of these really nice calculators that have all the nice sine, cosine, and tangent, this particular one, it is a background key, which means that in order to activate it, you've got to activate the shift key to get to it, as well as for the other root key. So one of the things they're looking at is, if you find the square root of 81, what should that be, guys? Should be 9, right? What is the quarter root of 81? That's a little bit different. If you were to type it into your calculator, let's see if I can pull the calculator up on my computer here. All right. So what times itself 4 times would give you 81? Well, this one's actually fairly easy to figure out. We know the square root of 81 is 9, yeah? So what's 9? What's the square root of 9? 3. So if I typed into my calculator 4 times, 3 times 3 times 3 times 3, what would that give me? Should give you 81, right? 3 times 3 is 9. If I do that twice, so I have 3 times 3 and 3 times 3, 9 times 9, 81. I said, I'm not going to do too much of that to y'all, guys. All right, so powers of powers. Now, this one actually will probably be used at least a little bit with some of the things we do. So 5 to the 5 cubed squared, okay, would be the same as 5 times 5 times 5 squared. I don't know why that's such a big 2. I think that was supposed to be exponential. But 125 squared gives you 15,625. The easier way is to multiply the exponents, and the answer would be 5 to the 6th. Okay. Like I said, that being said, I won't probably do a whole lot of that with y'all, because the main thing we're looking to do with a lot of this is more scientific and engineering notation. There's a reason for that. So raising a number to a fraction, now this one is actually just kind of neat. It's the reason I kind of go over it. Okay. The funny thing about raising a number to a fraction, when you raise a number to a fraction, so instead of 27 and 1/3, we do 27 and 2/3. This is the equivalent of saying 27, you're looking for the cube root, and then once that is done, you're going to square that. Just for future reference, if you happen to go into mathematics and you don't remember how to do that. Just to kind of give you an example of how that works. So essentially what you would end up with is the cube root of 27 is 3. I would then turn around and square that, so your answer would be 9. Answer is 9. Just to kind of give you an idea of that. again, it's not something we will be using almost any of. Just if you happen to come across a problem like that, that's how you solve that. Does that make sense? Just to kind of give you a reference, that's how you would solve it. The only reason I say that is some of y'all might get put into algebra. They might have a question or two like that. They might be put into taking a test and they say, how do you solve something like this? That's how you do it. Okay? All right. So powers of 10. Now this is actually very important. Why? Because guess what we'll be working with a lot of? Powers of 10. Powers of 10 are fun. So powers of 10 are used to express very large or very small numbers. Who's somebody that's really rich? And Bill Gates. Let's go with Bill Gates. Do you think he counts nickels and dimes? No, probably not. Well, let's put it this way. Do you think any millionaire, billionaire, or trillionaire in the world counts nickels and dimes? No, what do they probably count by? Powers of 10, right? They don't care that they're worth, let's say, $12,690,000 and $127.10. They don't care. They want to know they're worth $12 billion. They don't really care about the nickels and dimes. Right? That's for their accountants to keep up with. Just say. So by using exponents, we reduce the size of the number, right? Because we don't really want to have to sit there and look at a very large number because it just takes up a lot of paper, right? So one of the quickest examples we have, how many of you have heard numbers as thousands represented as, I want 1K? Well, believe it or not, that's a lot of what we're going to be expressing. Okay? You want something that's 1,000, you want if it's 1,000 pounds, if it's $1,000, I want 1K dollars. I want $1,000, right? We've actually turned into using the metric system these days. It's very subtle, but it is just slowly creeping its way forward. So for an example, 1,000 can be written as 1 times 10 to the third. And what that means is that it's 1 times 1,000, 1 times 10 times itself. Now here's the thing about, as long as it's positive tens, let me go ahead and throw that one out there. Excuse me. As long as it is positive tens, you can simply add up the zeros. Now if you're dealing with decimals and negatives, a little bit different, but the positives, you can always add the zeros. How many tens have I got? Well, how many zeros have I got? I've got 3 zeros, I've got 3 tens. Because 10 times 10 is 100, times another 10 is 1,000. Sound about right? Everybody following? Okay. So converting from positive powers of 10. All right, guys, I'm going to go ahead and say this, and this is going to be my mantra through a lot of this, and it's going to drive all of y'all nuts. But there is a reason I say that. And the phrase is, when in doubt, write it out. Okay? And the reason I say that, when we get into scientific and engineering notation, we are not dealing with a fixed decimal point. Much like you see right here, that decimal point has the ability to move. And it is very hard for a lot of people to wrap their minds around because it is it's not a concept we're familiar with, right? Because for us, our whole lives, the decimal point is what? The decimal point is fixed. The decimal point's not supposed to move. It's supposed to stay right where it is, right? So when that thing starts moving, our brain sits there and goes, whoa, 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 whoa. That's not supposed to happen. Because all our lives we've been taught that decimal point is fixed. So that's why I say, when in doubt, write it out. Because it gets you mentally in that space of the decimal point can move. Not only can it move, but the movement has meaning. Because it does. Okay? So the very first thing they're showing you here is 4 times 10 to the 2. And in order to write that out into its proper decimal form, they take that 2, 10 to the 2, and they move the decimal point from behind the 4. That decimal point is always understood to be where? Where do we always understand a decimal point to be? A decimal point is always supposed to be at the end of a number, right? That's where it lives. That's where it's comfortable living, especially in our minds. Anytime you write a number, where's the decimal point supposed to be? Whether we write it or not, it's at the end of the number. Does that make sense? So it should be right after the 4. So whenever I go to write it out, I move my decimal point back 1 and 2 spaces. And then I just move the zeros into place. So 4 times 10 to the 2 is 400. Okay? Like I said, this is a concept that a lot of people have trouble with. Why? Because that moving decimal point, our brain freaks out and goes, that's not supposed to do that. No, not supposed to do that. Unfortunately, that is the concept I'm going to have to teach y'all in this. Is that decimal point, you have to become comfortable with it moving. Why? Well, because we get into things like electricity and electronics, and a lot of the stuff we deal with are very big or very small numbers. The last thing you want to do is take up time by saying, and I'll just give y'all for an example. If I have a 12 mega ohm resistor, that actually means it's 12 million. How many of you want to write those zeros every time you've got to write that in there? Anybody? And I'll let you know exactly why we're dealing with a lot of this. So we're dealing not with, we're not doing this for fun. We're doing this because it takes very giant numbers and we shrink them. But the things we put with those are going to have meaning. Okay? Everybody with me so far? So my main rule with this is until you've got this in your head of moving that decimal around and being able to track the movements, when in doubt, write it out. Okay? And the whole reason of that is to get you used to moving that decimal. Because otherwise, it becomes very, very easy to get yourself confused at it. So for positive powers of 10, again, anytime you add 10 to the equation, you're adding a 0 to it. So 10 to the 1 is 10. Excuse me. Whoever invented allergies, it's an evil person. Okay, excuse me. 10 to the 2 means 10 times itself twice. In other words, 100. And so on and so forth. What you should notice, 10 to the third, 3 zeros, 4 zeros, so on and so forth. Okay? It's just tracking that number of zeros. Does that make sense? Everybody understand where we're going with this? Everybody comfortable? Everybody happy? No questions. One thing you might want to notice, 10 to the 0 has no multiplication. And in fact, 10 to the 0 is 1. That might be something you want to track yourselves. Might want to write that down in notes or highlight it or something so that you remember that. Because that actually is going to come up a few times. 10 to the 0 is 1. So if you multiply 10 to the 0 times anything, you're just multiplying by 1. Does that make sense? All right. For negative powers, this is for dealing with very small numbers. How many of you have ever heard the term milli or micro? Okay. So some of you have heard those. This is where that comes in. They're a negative power of 10. And I'll explain that in a little bit too. So by using exponents, we can reduce the size of the number because anytime we're dealing with this, what we're trying to do is just get rid of all the excess numbers. Who wants to sit here and write all these zeros and everything else? You want to write that every day? You want to have to write that all the time you're dealing with these problems? Everybody shake your head no, because nobody wants to do that, right? So what do you do instead? Well, we can wrap it up in a nice, neat little bow by moving your decimal. Again, this becomes the problem that a lot of people have with this, guys, so please bear with me. So the way that we tend to write these, I'll go ahead and kind of show you all this little trick. So we take the decimal and move it. Anytime we move that decimal, what do you think we have to do? You have to count how many times you move it. Okay? So I moved it 1, 2, 3, 4, 5, 6 times. And I did that because I wanted a positive number to deal with. Right? I don't want a decimal number to deal with. I want a positive number to deal with. I want a whole number, right? So I moved it 6 times. But since I'm dealing with behind the decimal, it's a -6. Does that make sense? Is everybody with me? Like I said, this comes back to when in doubt, write it out. This is going to make it a lot easier for y'all to kind of deal with some of this. So that being said, any questions on this so far, guys? All right. So if you're converting -10 back to itself, you have to do that with the understanding that you're starting behind the decimal to begin with. So when you go move it, you have to move it that same number you moved it to get to it, you have to move it back. So that's why you end up with 0.0047 in this particular case. Does that make sense? Like I said, I'm going to give y'all some homework with this, and on Tuesday I'll probably give y'all a bigger packet to do it some more. And I'm not trying to torture y'all with homework on this, guys, but this is one of those, everybody always seems to have an issue with the concept of this. I've had people that I start out at the very beginning of the mini term teaching y'all this, and at the very end of the mini term, and even past into DC, I have people that struggle with this, even with all the reference material I put out there. All right. So think of it not so much as homework, but as forced studying. I'll give you the paper to take on, but it's also on Blackboard. I'll tell you right now, the ones I give you as true homework, I don't generally expect back until we get to the final. And again, I just use it as enforced studying. It's forced studying. I try and make it a forced study. Why? Because it's technically homework and you have to do it anyway, but I'm just letting you have it as study material too. So that will be, I'll be giving that to y'all on Tuesday. But the one you're getting tonight is Lab 1. So for negative powers of 10, again, 10 to the 0 is still 1. The negative 1.1, negative 2.01, so on and so forth. You're just moving that decimal forward. All right. Now, how many of you remember whenever I was talking about those hidden zeros that we all know are there? This would have been back when we were dealing with decimals, right? We were talking about how in order to add, subtract decimals, what do? We create what? We create placeholders. Do those zeros have any meaning when we're lining up those decimals? No, they don't, right? They're just simply placeholders. The same thing works for this. Any number you can think of, even pi, well, to start with. If you're doing very simple numbers, in front of and behind every number, how many of y'all remember the old calculators that used to set up themselves kind of similar to this, where you had zeros across the calculator and the numbers were just put into those zeros? Do y'all remember those? Kind of, sort of? I'm getting blank looks from everybody, but okay. The whole purpose of these zeros is not that they have meaning. They don't have meaning till I give them meaning, right? So the whole purpose of it is as a placeholder. Well, the great thing when we're dealing with powers of 10 is the fact that when I move that decimal, I can then give these meaning. Okay? But they're still nothing but placeholders. They're just ways that I can move that decimal some more. Does that make sense? All right. All right, so on your calculator, there are different ways to do powers of 10. If you want help with your calculator at some point, let me know and we'll kind of look through it and see if we can figure that out. Adding powers of 10. Okay, so when adding or subtracting powers of 10, the exponents must be the same. So if we try and work the problem, 2 times 10 squared plus 3 times 10 cubed, we must change the powers of 10. And there's a couple of different ways to do this, guys. I understand that they have their way. I'm somebody that has my own way. And I'll show you why. And it goes back to that rule that I've been telling you for the last 5 minutes. It goes back to when in doubt, write it out. So first of all, anytime you come up with a problem, especially when you're first dealing with powers of 10. Easiest thing is when in doubt, write it out. So 2 times 10 squared. And we're adding 3 times 10 cubed. First thing I'm going to do is go to the when in doubt, write it out. Why? Because it lets me understand the problem at a better level. So this is 2, 10 to the squared means I've got 2 zeros behind it. So I have 200 plus 3, 10 to the third, so that's 3,000. All of a sudden I've got a better understanding of exactly what I'm looking at right now, don't I? All of a sudden it's a lot more clear. When in doubt, write it out. You get a better clarity of what you're actually dealing with. So there's a couple of different ways I can rewrite this problem to make it to where my exponents match. Okay? So the first way I can do it, I can say, well, my decimal's here. My decimal is always understood to be at the end of my number, yes? Okay. So if I have 2 times 10 squared, then I add, okay, so I need to bring this to 10 squared. Well, 1, 2. That would give me 30 times 10 squared. That would solve that problem, yes? But there's another way. Because I could still have 3 times 10 to the third. How do I get to the third? 1, 2, 3. I end up with 0.2 times 10 to the third. Everybody see how I did that? I have the ability to do the problem differently because I wrote it out. Okay? So there's a couple of different solutions to this particular problem. And we'll talk about the different notations when we get there. One is scientific notation. Some of y'all have heard of that, yes? And then there's engineering notation. I will go ahead and tell you now, the 32 times 10 to the 2 follows into neither category. The correct category and the correct answer for this would generally be the 3.2 times 10 to the third. That would solve for both. We'll get a little bit deeper into that as we go. A lot of people question my method of the when in doubt, write it out. But until you really get comfortable moving that decimal, I can tell you right now, just looking at this problem, the easiest way for my brain to have translated that was, oh, I can just take the decimal, move it forward. This would be times 3, this would be a 0.2, solved. Right? Because I've been doing this for so long. I understand that decimal is on the move. I understand looking at 2 10 to the 10, sorry, 2 10 squared, I know I'm looking at 200. But that's me. And I've been doing this for over 5 years. At least. Okay? I've been doing this a while. So my brain automatically can look at these answers and go, oh, that's easy. Move the decimal. You need to become comfortable moving that decimal and understanding that decimal is no longer a fixed point. Does that make sense? But I'm not doing this for my health. I'm doing it for y'all. I want you all to understand that that decimal has got to move. Well, that decimal has to move. Anytime you move it, you track it. Okay? Excuse me. All you're doing is you're tracking the movement of that decimal. All right, and the same applies for subtraction. Okay, so this one again, I'm going to go back here and I'm going to say, okay, let's look at this problem in its totality. So I have 3 times 10 to the 6th. I'm subtracting 2 times 10 to the 4th. Before I ever start messing with those exponents, what should I probably do first? Write it out. So I have 3 and 6 zeros. And then I've got 2 and 4 zeros. Okay. So I've got 3 million minus 20,000. Okay. Looking at this in the first place, it just looks like 3 minus 2, but you're actually dealing with 3,020,000. Okay? So there's a couple of different ways I can change this problem. Again, by writing it out, I give myself that room. So I could leave it as 3 times 10 to the 6th minus, well, if I do that, 3, 4, 5, 6. I'm going to have to use a 0 that's out here, just kind of hanging out here, right? So it's minus 0.02 times 10 to the 6th. That's one way to write that, right? Solves a few things. Make that very quick and easy to solve, wouldn't it? The other way I can write it is the way they've got, where you do 300 times 10 to the 4th minus 2 times 10 to the 4th. And still one more way to write it would be 30 times 10 to the 5th minus 0.2 times 10 to the 5th. There's so many different ways you can write this to solve it, right? And by writing it out, I give myself the freedom to move that decimal point wherever I want. Does that make sense? I can quite literally move that decimal point wherever I want. I know it sounds like a silly rule. You're going to get really sick and tired of me saying it. But I have found that it probably is one thing that works the best in trying to get your mind wrapped around this particular day. Why? Because it is something that is a concept. The thing is, what I'm about to start teaching y'all, not mathematics, nope. But the things we're about to start getting into is basically a new language for you. And that new language is going to be based off of mathematics, specifically these mathematics. So these are kind of here to stay, and you kind of need to get used to them. Is what it is. Any questions on this, guys? All right. Huh? Yes. All right. I'm going to give y'all a few minutes to work on this particular set of. Did everybody do all right with it? Anybody got any questions on it? Before I start going through the answers. All right, so the first one, we have 6 10 to the third plus 2 10 to the third. That should have given you 8 10 to the third. Yes. Sure. I'll take a look at it here in just a minute. So just to kind of give you all an idea, these are the solutions for these particular ones. Does anybody have any problems with any of them? Excuse me. What you got? Yep, that's right. Okay. So does writing it out actually help as far as the knowing how to work with it and understand it? I'm going to show you why it's even more important here in a minute, because when we actually get into some of the things we're going to be getting into, you'll see why I tell you to write it out. Yeah, it's a little more complicated. So while y'all are writing this down, I'm going to go ahead and say take one pass around. What I am sitting around is lab 1. All right, this is a take-home lab that is all about powers and roots. Okay? Some of them didn't get stapled, I'm sorry. I have a stapler up here that I can send around to you. There should be one for everybody at least. And one of the biggest things you'll see is not so much adding and subtracting as multiplication and division. Again, we'll talk about why that is. Biggest thing of all will be conversion. Being able to convert one number into others. Is everybody good with the adding and subtracting page here? Does everybody need a minute? Those my leftovers? Okay. I think somebody, nope. Yep, somebody's missing a page. It should be 3 pages, I think. Anybody only got 2? Yeah, the copier's kind of been hitting this lately. It's annoying, but there it is. All right. So multiplying powers of 10. So in multiplying powers of 10, it's pretty easy, actually. Well, I won't say it's totally easy, but let me kind of give you an idea of this. This is why it goes back to that writing it out. So here we've got 100 times 10 to the 5. And then we're multiplying it by 2 times 10 to the third. Now, personally, I don't like multiplying by 100. Why? Because I can simplify that even shorter, right? So my way of looking at it would be 1 times 10 to the 7th times 2 times 10 to the third. How did I make that happen? Because I moved my decimal point forward 2 places. By going back to the writing it out, that is my original number. So in order to shorten that number so that I only have one number in front of that number, move it forward 7 places, and every time I move that decimal, I count it. All right, I count my decimal movements, which would then give me 1/10 to the 7th. So what I end up with, if Y'all remember in fractions, what did we do with the whole number versus the partial number? We split them, right? You do the same thing here. So I end up with 1 times 2 and 10 to the 7th times 10 to the 3rd. Now the funny thing about exponents is that when I go to multiply them, I'm adding my exponents together. Okay? So you can kind of flip that over just a little bit and it becomes an at addition sign. So what I should end up with is 10 to the 10th. So my overall answer should be 2 times 10 to the 10th. Does everybody see how I did that? Does everybody see how I did that? So it goes back to that when in doubt, write it out. The only reason I say that is because I want y'all comfortable with moving that decimal. Like I said, for me, as long as I've been doing it, I can automatically look at that 110 to the 5th and say, well, that could become 110 to the 7th. Because I've been doing this so long. I'm comfortable with it. Most people don't see that. Why? Because it is still so foreign to most people to say, I can move that decimal. Right? How many of y'all are already comfortable moving that decimal? Quick raise of hands. Like 2 people, 3 people, 4 people? Most of y'all will not be comfortable until we really get into this. Because it does take a little bit of mental gymnastics until it becomes easy. Until it becomes second nature. Okay? Okay. Now see, the way they do it is they left it at 100. Well, just like with fractions, you end up simplifying a lot of this. As for division, so instead of multiplication, we've gone to division. Same number, so I'll leave most of this up here. So I have 100 times 10 to the 5th divided by 2 times 10 to the 3rd. Now, the last time I went ahead and shortened that 100 down to 1. You think I probably need to do that with this one? No, because I can't divide 1 by 2. Right? So again, it comes down to, I'm still dealing with $10 million. Essentially, I'm just dividing it by 2,000. Okay? But in this case, what I'll bring this down to is 10 times 10 to the 6th divided by 2 times 10 to the 3rd. Because I can divide 10 by 2, but I can't divide 1 by 2, right? That won't work. Never does. Okay, so I'll separate them out and say 10 divided by 2, and then 10 to the 6th divided by 10 to the 3rd. 10 divided by 2 will give me 5, and if I multiply, I'm sorry, if I add for multiply, what do you think I do for divide? You subtract. Thank you. So I'll have 6 minus 3, which would give me 10 to the third. So my overall answer should be 5 times 10 to the third. Does that make sense? So you add for multiply, subtract for divide. Does that make sense? And believe me, you'll be doing a lot of all this. So 50 times 10 to the 2 or 5 times 10 to the third. I like to go for smallest number overall. That's just me. All right, so there are 3 different ways we can write powers of 10. And I was kind of talking about this earlier because I tend to find it really funny. How many countries are there left that they're still using imperial system, which is what we use here in America? Liberia, Myanmar, and the US are the main ones that still use imperial. And then you have Great Britain that just kind of does whatever they want. No, seriously, they don't use like really either one. They kind of use a hybrid system of whatever they want to do. Yeah. So there are 3 countries that still use imperial. The rest of the world uses metric. That's kind of strange, isn't it? We are the last major country that still uses imperial. So with powers, the whole reason is because it's all based on 10. But the powers of 10 that are used, you have scientific notation, engineering notation, and metric prefix. And guys, you definitely want to know about all 3 of these. A is going to be on that lab. B, great test questions. So scientific notation. I'm going to put this on the board because I want to make sure everybody kind of realizes exactly what the difference between these are. And I want y'all to write these in your notes. And I want y'all to make sure you know this by heart. Simplest terms about scientific notation. You will only ever have one number in front of your decimal. Only one number in front of your decimal. Now, there's a reason I'm making a big fuss about that. Okay? So the number in front of the decimal will go between 1 to 9. Okay? Number in front of that decimal will fall between the numbers 1 and 9. Okay? Everybody follow me so far? A lot of this is great and all that, but I'm going to summarize it by saying this. The exponents will increase and move by 1, and the number in front of that decimal will fall between 1 and 9. Okay? Excuse me. Everybody following me so far? Like I said, this is all great information. Summary is that you will only have one number in front of that decimal. It will fall between 1 and 9. And that exponent will increase or decrease in increments of 1. Does that make sense? And that will all become a little bit clearer when we get to engineering notation. All right. So knowing what you know, converting each to scientific notation, just to kind of get y'all started, what would be the first one? 82,000. Any clue? Well, my decimal point starts where? It would be 8.2 times 10 to the fourth. So just to kind of get y'all started with that one, let's see what y'all do with the rest. So just to kind of go ahead and translate these ones that are fractions for you. You'll see why in a minute. I got an answer. Is that what you mean? Yes. Yes. That's what I meant by you have to have a number between 1 and 9 in front of your decimal. 0 is not acceptable in front of the decimal. Only one number in front of the decimal, and it must be a number between 1 and 9 in front of the decimal. Those are some loud cicadas. Not just 6. times 10 to the negative 1. Anytime you move the decimal, you have to count it as a power of 10. Does that make sense? Anytime you move that decimal. And I will tell y'all one other little secret, and it has to do with numbers that fall behind the decimal, or just numbers in general. The funny thing about the human brain is that we like to group things. Y'all know what I mean? Kind of.
The easy way.
The way we work is visually, this number right here, how many of y'all are looking at that and going, I have no idea what to do with that? Now, what if I did this? Section them off into groups of 3. Visually, does that help you? All of a sudden your brain goes, oh, huh, that's not what I thought it was, right? Doesn't actually say it verbally, but all of a sudden your brain kind of looks at that and goes, that's a lot more understandable than looking at a bunch of zeros and numbers, right? Something I have found, there have been studies done about this and things like that. It's just always kind of funny to me is we have to have studies to be able to know that we understand something. There's always got to be a study, right? Why do people learn? Well, they go to class. Hey, that's a concept. But the whole reason is that we as humans, we have like to break things up. Okay? The more you put into something and stuff into something, the more our brain just sits there and goes, I cannot count that. Okay? So if you break it into smaller groupings, all of a sudden it makes it a lot easier for your brain to sit there and go, oh, I can see the difference between these. Does that make sense? So anytime you come across a giant number and you just visually cannot break it up, physically break it. All you've got to do is go in, put commas, put a visual barrier between them, whatever you got to do. And mentally it helps you. It seems kind of silly to do it, but believe you me, I've used that on many mathematics. Why? Because visually I don't like having a jumble. It puts it in an order for you. Now, why break it up into 3s? Well, because what do we understand about 3s? Why do we put money in groups of 3? Because visually it breaks it, right? Anytime you're writing money, anytime you're writing in front of that decimal, what do you put? You start putting commas, right? Why? Because it visually breaks it for you. Why we don't do that behind the decimal or find some way to do that behind the decimal, I've never figured out. But there you go. All right. Everybody done with this? Everybody ready to move on? Okay. I'm going to erase what's on here because it's going to pop the answers up here in just a minute. Oh, for God's sake. For those of you that can't see it, hold on just a second. Let me fix this. Now that's going to bug me. There we go. Nice and neat. So 8.2 times 10 to the fourth, 3 times 10 to the third, 2 times 10 to the negative 4, 6 times 10 to the negative 1, 2.43 10 to the fifth, 7.5 10 to the fourth, so on and so forth. Did y'all do all right with those? Sorry. Because every time you move that decimal, you count it. One, two, three, 4, 5. Move that decimal 5 times, you count it 5 times. If nothing else, think of it. Do you remember how you learned initially Do you remember learning your numbers initially like this? Yeah, same thing here. Because you're moving it by a power of 10. Every time you move that decimal, you're moving it by a multiple of 10. Does that make sense? That's why we count those up and those become our exponents. Does that make sense? Any more sense to that? Okay. So, everybody good with these? So let's talk engineering notation. Now, engineering notation's kind of interesting because we talk scientific, that's one number in front of the decimal. Engineering moves in multiples of 3. All right, which means that the number in front of the decimal falls between 1 and 999. Now we're change something up right here. Your exponent moves in multiples of 3, and the number in front of that decimal will fall between 1 and 999. I'm going to give you a good rule of thumb, that's follow the comma. Now, here, a lot of you sitting there going, follow the comma. Follow the comma. When it comes to engineering notation, follow the comma. I don't care if it's in front of that decimal or behind it, follow the comma. You might have to put it in yourself. But just like you do with money, how do you break money? You break it into sections of 3. So if you start doing that with your number in front of or behind the comma, you can follow the comma for engineering notation. Do you understand what I'm trying to say? So I'm trying to figure out exactly how to say this in the most easy way. Okay? I don't know who wrote this slide, but follow my rules right here. And you should be fine with working with these. All right. So looking at your number comparisons, for your base number, if you have something like 33,000, scientific, we already saw, would have put that at 3.3 times 10 to the 4th. Why 10 to the 4th? Because you moved that decimal 4 times. With engineering, like I said, follow the comma. My comma falls before, and that's the furthest comma that I got on my document, which means that I've got 33 times 10 to the 3rd. I'm moving for my exponent, I'm looking for a multiple of 3. So that exponent will move as a multiple of 3, 6, 9, 12, 15, 18, so on and so forth. Does that make sense? That is what you're looking to deal with. Same thing goes for behind the decimal. I don't care what numbers I've got back here. I'm going to look for that first section so I can get numbers in front of my decimal. I'm going to follow the comma, right? For scientific, I just need one number in front of that decimal. That would give me 4.5 times 10 to the negative 2. For engineering, I'm moving by multiple of 3, which would give me 45 times 10 to the negative 3. Does that make sense? Any questions? Okay. All right, so looking at these for engineering notation, I will go ahead and work one for you, and that's this guy down here, number 4 over here. I know there's a lot of confusion. Because how are you supposed to take something that's only got one movement behind that decimal? How can I possibly have a power of 3? This goes back to that. You understand that there are zeros out there, you just don't ever use them, right? Not in front of.
Oh, that's what I meant.
Move it 1, 2, and 3. You would end up with 600 times 10 to the negative 3. Y'all see what I just did? Anybody have questions over what I just did? So with every number, there's understood to be zeros both in front of and behind it. We don't use them, but they're there. We don't have meaning for them unless we use them, right? They just kind of hang out. They're the invisible zeros that are around every number. So when using things behind the decimal, we can borrow some of those zeros to use in our numbers so that we can make it a power of 3. So for this particular one, we borrowed 2 of those zeros that are out there, and we're able to give ourselves 600 times 10 to the negative 3. I swear if I drop this pen one more time, I would have dropped it about 10 times tonight. So to give you another example, this guy right here, again, following the comma, right? Group everything in groups of 3. If I move it that first set, do I have a number in front of my decimal? No. I only have zeros. Can I have zeros in front of the decimal? No. So move back one more. This would be 200 times 10 to the negative 6. Does what I did make sense? Always a better question to ask. No. Anytime you're moving this, you're looking for only your. Okay, let me go back to this. The numbers must fall between 1 and 999. I'm moving in groups of 3. That's only got 0. Second one, I've got a 2. Does 2 fall between 1 and 999? Then I've moved the furthest I need to move. It'd be 2.56 times 10 to the negative 6. Okay? The number in front must fall between 1 and 999, and it must be a multiple of 3 in the exponent. Does everybody see how I did that? Are there any questions? Have I managed to completely mystify everybody? All right, so the first one should be 82 times 10 to the third, 3 times 10 to the third. And I'll go ahead and tell you this, guys. Scientific notation and engineering notation will occasionally intersect. but not all scientific notation will be engineering notation. And not all engineering notation will be scientific notation. Does that make sense? They intersect at points, but they will not they're not the same thing. Does that kind of make sense to everybody? So on and so forth. Just to kind of give you all the answers for those. Give you an idea of what those answers should be, guys. Does everybody kind of follow along with the pattern here? Okay. All right. Everybody good? I'm going to go ahead and erase all this, and we're going to move on. And there's all the answers again. All right, so I'm not even going to kind of go into that. Let's talk about metric system and why we are the last of 3 countries that are holding on to the imperial system. And this is kind of where I step a bit on a soapbox. I'll tell you why. First of all, we have not converted over. So we were supposed to convert over. I think my parents were talking about the 70s and 80s. They were trying to do a conversion over. You still see some signs out there that have kilometers on there. You know the reason why we didn't? Too expensive. That is purely the reason why we are still in imperial. It was too expensive to switch everybody over at the same time. So he just kind of said, forget it, we'll do, you know. And these days it's just kind of creeped gradually into what we do. So the metric system is easier than the English system, and it is very consistent. It has one value for length, one for liquid weight, one for dry weight. Now, how nice would that be? How many of you all cook and have to go through the measurements and ask yourself, what exactly am I trying to measure? Wouldn't it be nice if everything was the same? So weights and measures. Let's kind of look at what we have. We have inches. Now, who decided what an inch was? Who decided? The story behind a foot is that they actually used somebody's actual foot. Really? Huh. Well, that seems a little inconsistent considering that my foot's not the same as any of y'all's feet. I don't think any of y'all probably have the same shoe size, right? Everybody's going to have a different shoe size. Everybody's going to have. So how are you supposed to use that as consistent length of measure? Seriously. You know? How many of y'all have ever heard, well, that right there is 3 acres? What is an acre? Seriously, ask yourself. It's not consistent. Kind of like, what is a city block versus a regular block? I'm seriously, start listening to how people measure things off. You can just go up 3 blocks. Okay. What is a block? Am I talking about a building? Am I talking about 3 buildings that are all just considered one block? What? Think about that. How aggravating is it whenever somebody tries to give you directions and you sit there and just go, It's like somebody sitting there going, oh, you just go up, down, and go by the cornfield and turn left by the old gas station. Well, I think it might be a Citgo, but it might be a Texaco. And of course, you're passing by a Texaco, and then you pass by a Citgo. I mean, seriously, you have to sit there and ask yourself, who created all this? And then you have surveying. If you're doing surveying, you have leagues. What is a league? What is a furlong? Seriously, they have these terms. Okay? What is the length of a chain? Okay, are we talking about a boat chain? Are we talking about a jewelry chain? What are we talking about as a chain? Yeah, if you ever start in conversations with some people, you have to sit there and go, okay, it's like you're trying to speak to me. I know it. Then you have the nautical lengths, fathoms, cables, nautical miles. What's the difference between a nautical mile and a mile? What is the difference between those? And how do you measure that? Hmm? We will, yeah. Here's the liquid. Funniest one I've always found is, what is a hogshead? Seriously, what? And what is the difference between a barrel and an oil barrel? Some of these you've probably heard of. Personally, I've never heard of a gill or a jigger. So this kind of becomes very funny because this is all about imperial. Now you see why somebody said, I'm going to come up with something simpler, right? Because how are you supposed to measure off an oil barrel versus a barrel versus a hogshead? I seriously want to know how a hogshead became a unit of measure. What, did somebody take the head of a pig and say, this is going to be how I measure this? Now that's a visual stick in your head, won't it? Then you have dry ones, okay? Hundredweights, tons, pounds. Again, you come back to drams and grains, barrels, bushels. What is a bushel? What's a? And then you get to the Peter Piper picked a peck of pickled peppers. What's a peck? Seriously. Okay. Seriously, still, who came up with a hogshead? So, again, this is why you sit there and go, okay, this is a really messed up system. And for those of you that do not know what a troy weight is, that has to do with fine, troy weights are all about jewelry and fine metals. The only reason I know this is because I personally buy my own jewelry and all my chain and my wire from certain places, and they sell them in troy weights. Well, then you have to sit there. Seriously, I buy it in lengths. I do not buy it in troy weights because I still do not understand the system of this. Okay? The troy weights are how you buy jewelry and the fine metals. Versus the three basics: meters, liters, and grams. Okay? Wouldn't it be nice to have a system of three? And believe it or not, this has snuck its way into the US. How many of you buy the giant things of soda? The giant jugs of soda. What do they come in? 2-liter bottle. I think that sounds a little familiar here. It's kind of snuck its way in. Most of our drinks that we buy as a liquid, what do they come in? They're measured off in liters now, right? It's getting to where we start measuring things in grams. Still haven't quite gotten converted over to meters yet, but we're kind of making that way towards it. Little by little, excuse me. Excuse me. So metric prefixes. Real quick, how many of y'all remember the old phrase? In fact, you might have learned it in early math class, science class, one of the two. The King Henry danced merrily drinking chocolate milk. Y'all don't remember that at all. Probably a different version of it, right? It should have been something along the lines of should have been those initials. Learn some form of something that was to learn basic metric. Kind of remember that? Should have been somewhere around 5th, 6th grade science class, chemistry class. Now that's mathematics. Please excuse my dear Aunt Sally's mathematics. This was supposed to go with scientific. And the whole reason we go there in science and engineering is because we as the U.S. are not alone in what we do in the world. Give you for an example, if somebody comes over from, let's say, Japan or Germany or anywhere in the world, right? They have to be able to work the same jobs we work, right? So a lot of the fields that involve technology, let me actually try and say that word again. Any field that involves technology, science, basically STEM. Y'all know what STEM stands for, right? Science, engineering, technology, and math. Y'all have heard that term, yes? So basically any field that involves those four has pretty much been taken over by metric. Why? Because it's a worldwide language now. Does that make sense? So the way we've kind of got this going, believe it or not, is kind of interesting how we've got this. So symbols are used to represent the most commonly used powers of 10 in notation. Specifically, we have tied it off to engineering notation. Why? Because engineering notation makes everything easier to write. Okay? So with engineering notation, we've kind of gotten rid of a few of these. We've added some different ones. I'm going to write them on the side of the board here. Wish I was a little bit taller, but y'all have to kind of use your imaginations. Yes, that's a G. And so you have hard drives. You never heard of a terabyte? It's been around for a couple of years. It's just now getting cheap enough for everybody to actually buy it. Mm-hmm. Yeah. Well, it's just now getting cheap enough that everybody can buy it, and it's. Let me kind of put it this way, as far as um, how to say this. They're not going to put stuff on the market if they can still squeeze a penny. Does that make sense? They can still squeeze a penny out of somebody. They're not going to upgrade the market yet. Whenever it becomes more mainstream and people have bought more and more of the high-end expensive, they drop the price so that they can start selling a newer version of it that's supposedly even better. You know what I mean? Hmm? Yeah. It's kind of like, why does a light bulb not last for? There are light bulbs that have literally lasted for 200 years. Why can we not still buy those? Well, because it wouldn't make anybody money. No, seriously, there are light bulbs that are like 100-year plus light bulbs. You can look it up. There are light bulbs that have been burning for over 100 years, but yet we can't buy them. They won't make them. Why? Because it means nobody'd make any money. It's a very stupid, very aggravating business practice, but it is what it is. Okay? Yep. So that's why you're just now really starting to hear terabyte. Terabyte hard drives have been around for at least 5 to 10 years that I know of. They've been around a while, but those would have been, if I remember right, when they first came out, they were about $1,000. Yeah. Those would have been they were separate hard drives that you could buy. There were 1 terabyte hard drives for about $1,000. Yeah, now they've dropped down to about $100 to $200, and you just sit there and go, why? Yeah, but it's kind of like, why have we now gone from a kilobyte thumb drive to you can't even find a 1 gigabyte thumb drive anymore unless you're buying it off Amazon. If you go into any tech store, what is the minimum gigabyte thumb drive you can buy? Between a 2 and a 4. Those are generally about what, $10, right? Why couldn't we sell them cheaper sooner? Well, because they wouldn't have made any money otherwise, right? Kind of how business works on that. All right. Let's kind of go back to this. Focus. Squirrels. All right. So we use symbols to represent the most commonly used powers of 10 in engineering notation. So each letter or symbol represents an engineering value. You have milli, which is written as a lowercase m, and some of you might have even heard of milliamp. Anybody ever heard of the term milliamp? You'll learn what it means. You also might have heard the term giga, if nothing more than a gigabyte thumb drive. Okay? That's it. Kiss. Some of these terms might be familiar. Most of them won't, but by the time we get through with this class, they will. Everybody good? All right. So here's the metric table. It's the same thing I've written out over here to the side, only in reverse. So you have pico, which we've heard the term pico, but not really used in this context. Because most of the time you hear the word pico, you think pico de gallo. right? Or things like that. What it means is it's a very, very small. Oh my God. Okay. Focus. You've probably heard the term nano. It's nothing more than something like along the lines of a nanobot, right? It's supposed to represent something very small. Micro, which the symbol for micro is a very interesting one. I've kind of tried to draw it a little bit on the side here. The symbol for micro kind of looks like a U with extra legs to it. It's kind of got a tail to it. Something along the lines of that. Okay, I'll go ahead and tell you now. As long as you get something close, you could do it where one leg's long, just whatever you need to do to make it look like a micro symbol, or just to differentiate it from mega or milli. That's fine by me. Because there is another symbol that is a U. I can't remember off the top of my head. Seriously, you can look that up through Wikipedia or Google it or whatever. These are the ones we mainly use because they're the ones we mainly use. But there are others. I know one of them is called EXA, E-X-A. And it's a bigger than a tera. So, yeah, there's a lot of them out there. So, you have pico, nano, micro, which a lot of y'all have heard micro, if not other than something called a microde, right? Micrometer, all sorts of things. Milli, you've probably heard 1,000 times. Kilo, kilos should be very familiar because we use kilo all the time. It's in pop culture, it's in our basic culture. Anytime somebody's dealing with something in the thousands, they've come around to replacing it with kilo or K. Sound about right? Okay. Then you have mega. Y'all probably heard mega 1,000 times. In this context, it actually means something in the millions. Giga, gigaton, huh? Yeah. So you have giga, that's billion, and then you have tera, that is trillion. Okay? And these are the symbols for them as well, guys. There is no prefix in metric for the numbers between. I'm going to back that up. There is no engineering prefix associated with a metric prefix for the numbers between 1 and 999. The reason I'm prefacing that is because there actually are metric prefixes for that, but they're not ones we use with engineering notation. Okay? So there are others that are between the 1 and 999. They're just not the ones we use. Okay? Does that make sense? Okay. So these are the main 8. You might want to go ahead and start memorizing those. They will be used quite frequently. Yes. That's kind of why I wrote them the way I did. Micro, again, is kind of a U shape, just with a longer leg. I don't know how else to describe it, okay? Huh? Micro is one of those that it's a very distinct shape in and of itself, but at the same time, it can be a pain to make. done with either leg running long. I've seen it done 1,001 different ways. As long as you can differentiate it clearly between milli and mega, that's fine. Okay? As long as you can differentiate it between milli and mega, that's fine. It's kind of the aggravating thing about it. All right, everybody good? All right. Not really. That's the one thing I don't like about that book is that it does not cover metric prefixes. Yes. Because that particular book that's for this class is not just for this class, it's also for DC and AC. I've got it right here. It's Electricity Electronics by Schoolcraft Publishing. Hydraulics, pneumatics? Yes. All right. What time is it? All right, we good with this, guys? We're gonna keep moving. Guess you can take a picture. Here. Just kind of slide that your way. All right, so you already should have the engineering notation for these. All you need to do is match up to the metric prefixes. So all you need to do is match your engineering notation to your metric prefix. For example, this one right here should be 82 kilo. You can either write it out or use the symbol. That's the great thing about using the symbol. You do not have to write it out. Micro. Because that's milli, that's micro. -6.
Oh, the stick and zero behind the 2 is trying to kill micro, right? See, I didn't know, see, I didn't know we had to do that. Electricity slash electrical. In this situation. That certain box on the right, I didn't know we would have to like fabricate it so we can come out with that number right there.
Well, that's how you were doing engineering notation, right?
Yeah, you can.
So for this guy right here, would be 600 milli. You can just write the symbol, as long as you know the right symbol. No, the capital M is mega. You can either write out the actual word, as long as you can differentiate between your M's as uppercase or lowercase, that's fine. You need to make sure you can differentiate between the two because there should be differentiation. Does that make sense? Yeah. While I'm thinking about it, I'm gonna go ahead and yeah, cause I kind of got caught up in doing this. Okay, I guess I'll wait till he comes back and we'll take attendance. Yes. Huh? 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 No, I have no control of the air in this building. That is totally somebody else. I turned off the pneumatics air. That was that giant compressor that was making so much noise. All right, guys, if y'all would please listen up for your name, I'm gonna call roll. Blanchard. Okay. Cherry. Garcia. Golden. Johnson. Cooley. McCord. Okay. Olette. I said it right, didn't I? I'm sorry. I keep trying. Okay, I know Pruitt's on collaborate with us. Temple. Thomas. Whitaker. And White. Mr. White. Nope. Okay. Okay. So let's take a look at this. And there are the answers for this particular set. Just like engineering notation, these follow the comma. And here's a nice little table for y'all to kind of get an idea of what this is about. So, one of the things y'all need to make sure you do is work on the lab I gave you. Please do not lose that. I will give y'all about a week to work on it and make it due next Thursday. Okay? That way, if y'all have any questions, I can ask me. Yes.
You still want us to do the fraction and decimal things you got on there?
What you make, the main thing you need to do to make sure I got it are these right here, quizzes, and then your first three quizzes and agreements that are here in all those. Okay? Yes. Those, I'll go ahead and tell y'all now, guys. Those math quizzes I showed y'all earlier. Give me your attention for just another couple of minutes, guys. Those math quizzes I showed you earlier, those make up your test. Use them to study. Your first test is coming up. All right, I will probably do one more night of powers and roots. If y'all feel y'all are ready after that, we will go ahead and do test 1 Thursday, or we'll do it the following Tuesday. But test 1 is coming. Yes. sooner rather than later. If nothing, I give you guys, I'll tell you right now, y'all have multiple chances to take those quizzes. Go ahead and pause this out. Okay, y'all have multiple chances to take those quizzes. There is no reason you should not be able to pass them. Okay? So that being said, please go ahead and be working on those. All right? They make up your test. No reason you shouldn't make 100 between the two of them. All right. So work on that lab. Be back on Tuesday ready to work through powers and roots, and y'all have a great weekend. Huh?